Okay, good morning. So we continued the lesson. We talked about triangles quite a lot. Now we just switch the topic a little bit. Of course, we will be involved with triangles all the time, more or less. But we want to talk about quadrilaterals today. Yes. So quadrilaterals are actually shapes that are bounded by 4 line segments. And then we talked before, if you have watched the videos and remember, so we have a type of a quadrilateral. So this is a quadrilateral. You don't need to have some specific rule for quadrilateral, but one thing that I want to mention, if you want to name a quadrilateral A, B, C, D, then you have to decide either to go clockwise or anti-clockwise all the time. So you are not allowed to write A, B, C, D, because in geometry texts, when they write you have a quadrilateral A, B, C, D, by convention they mean A and C are opposite, B and D are opposite. So this is the convention that you have to respect when you read the text in geometry. And then we have 2 types of quadrilaterals. This is called the convex one. Yes, and we can also have a concave one. We talked about these things 1, 2, 3. So let me make it a little bit more clear. So that is also a quadrilateral. We talked a little bit about these things before. Today we want to consider, that's called concave, or sometimes non-convex quadrilateral. Okay, so here we just want to talk about these type of quadrilaterals. Of course, one thing that you know that is true for both of them is the sum of the interior angles. Yes, it becomes 360 all the time, even for this case. Okay, but now we have some type of quadrilaterals that we want to talk about. One of them is called, in British English they call it trapezium. But in American one they call it trapezium. Yes. So it's a quadrilateral that has 2 parallel sides. Of course they can have more. I mean, so if you have a quadrilateral, so something like this. This is a quadrilateral. It consists of 4 shapes. And by the way, I didn't say what is the convex. So the convex means that whenever you choose any two points interior to the quadrilateral and then you join them, every point on this line segment lies in the interior to the quadrilateral. For example, in this case, if I choose this point and that point, and if I connect them, some part of that is outside. Yes. So that's why we call it concave. But it doesn't matter which pair of points I choose, and when I connect them, all the line segment generated in that way will lie inside the quadrilateral. So that's why we call it convex, that one concave. So that's also a convex quadrilateral. And then I have a pair of parallel sides. At least I should have a pair. Okay, so that's called a trapezium or trapezoid. I will use this word from now on. Okay, and then we can have different types. So if these 2 lines are of the same size, we call it an isosceles trapezoid. Okay, but these are minor things. So this is one quadrilateral that you need to know the name of. Okay, another one which is very famous, then we have to deal with it. So that's a parallelogram, yes? A parallelogram is a quadrilateral. The definition is that you have 2 pairs of parallel sides. So when I give you a quadrilateral and I ask you to prove that this quadrilateral is a parallelogram, if you want to follow the definition, you have to show that these 2 are parallel. You have to also show that these 2 are parallel. Yes? That's a parallelogram, yes? Okay. So which one is which? Is a trapezoid also a parallelogram, or a parallelogram is a trapezoid? Or neither, or both?
Parallelogram is trapezoid.
Yeah, parallelogram is a trapezoid, yes? Because for being a trapezoid, I need to have a pair of parallel lines, yes? When I have a parallelogram, I have a pair, but I have more than one pair, yes? It doesn't hurt. So every parallelogram is automatically a trapezoid, but not the other way around. Yes? Okay. And then probably another famous quadrilateral that you know is what? Is the rectangle. So remember, when I ask you to prove a quadrilateral is a trapezoid, you have to convince me that you have a pair of parallel sides in that quadrilateral. When I ask you to prove that a quadrilateral is a parallelogram, for the time being, you have to convince me that I have two pairs of parallel sides. Yes? But now, let us go back, let us go to here. A, B, C, D, a rectangle. Yes? So what is a rectangle? A rectangle is defined to be a parallelogram with one right angle. Of course, automatically all the angles become 90 degrees, but that is what you need. So a rectangle is a parallelogram so that one angle is 90. Of course, then it turns out that all the angles have to be 90. We will come to these things, okay? But I just want you to have the minimum way. So if I ask you to prove a quadrilateral is a rectangle, you first prove that it is a parallelogram, meaning that for the time being you prove that these two are parallel, and then you prove that one angle is 90 degrees. Then it means that you have proven that the quadrilateral is a rectangle. Yes? Okay. And then what about square? So which one is which, by the way? Is a rectangle a parallelogram or a parallelogram a rectangle? Based on definition, a rectangle is already a parallelogram with more properties. It's more symmetric, yes? Okay, what about square? What is a square? So if you have A, B, C, D. So a square, you can say a square is a rectangle with an extra property. So a rectangle is a parallelogram with an extra property of having one angle 90 degrees. Now you can say a square is a rectangle with one extra property. What that property is?
All sides are equal.
Pardon?
All sides are equal.
All sides are equal. Yes. So this means that every square is a rectangle. Every rectangle is a parallelogram, but not the other way around. Yes. And every, of course, parallelogram is already a trapezoid. And then we have also another one, so it's called square. And then we have rhombus. Yes. So what is rhombus? So rhombus is a quadrilateral with all sides equal. So it's hard to draw these, so I mean that all these sides are equal. Of course, we can have different properties for rhombus. By the way, I forgot to write E here. So these are the famous quadrilaterals that I want you to know the name, and then we try to discover some properties of them. And you have to memorize them and use them. You don't need to prove them every time that you want to solve a harder problem, yes? So the first thing that I want to talk about is this. It's a theorem. It's a simple theorem, but it is instructive, I think. So, the following statements are equivalent. Okay, I will talk about this word in mathematics actually. So number one, if you say A, B, C, D is a parallelogram, or you say that AB is equal to CD, and AD is equal to BC. Okay, so you can phrase it like this: opposite sides are equal. Number three, angle A is equal to angle C, and angle B is equal to angle D. Opposite angles are equal. I'm a little bit sloppy. I should say that opposite sides have the same length, and then opposite angles have the same measures. But that's what I mean. And number four, this is important. AB is equal to CD and parallel to it. Yes. A pair of equal and parallel. So let me write it in this way. Opposite sides are equal and parallel. Yes. So any one of these is equivalent to the other one. So what is the meaning of being equivalent? So you know that, let me just tell you another example. This is a very famous and understandable example. If I tell you that x is equal to 2, you can conclude that x squared is equal to 4, but not the other way around, yes? Because if I tell you that x squared is 4, you cannot conclude that definitely x is equal to 2, because it might happen that x is equal to minus 2. So you can go in that direction, but not in the other direction. So mathematically speaking, this is statement. By the way, a statement, when I use a terminology in mathematics, a statement is a declarative sentence which is either true or false, but not both. Okay? So it's not exactly a statement here, but let us say that x is a real number, then x equals to 2 implies x squared is equal to 4. But I cannot go back I cannot go backwards, yes? So this means that these two statements are mathematically are not equivalent. This is something else than this one. This has more information to it. So the information, or whatever you want to see, they are not equivalent. But if I have x equals to 2, and this implies that x to the power of 3 is 8, and then of course this is reversible as well, because if x to the power of 3 is 8 and we are working in real numbers, then x is definitely equal to 2. So this means that I can go back and forth, and these two statements are now equivalent. Yes? Yes, is that understandable? So that's the meaning of the statements to be equivalent. So in principle, if I want to give a proof for this theorem, okay, so what is your idea about how to do that? Because in principle, there are many things that I have to consider if I want to do like this. So what I have to do, in principle, this theorem is a quite number of theorems, yes? I should say that ABCD's parallelogram implies this, and I should show that this implies that. I don't know. I need to check this implies this, this implies that. So there are many combinations that I have to consider. But there is an easier way to do it. What is that? Do you understand that? If I want to prove all possibilities, I want to show that from each statement, you can conclude the other statement and the other way around. So you need to consider a lot of cases, which is really boring because of such a simple theorem.
Yeah, we don't need to prove every like combination. We can just make sure that each of the statements can can go to another statement or can imply another statement. And then if we like make sure.
So may you speak more practically? For example, let us have three statements: P, and I have Q, and I have R. If I want to show that these three statements are all equivalent, I have in principle prove this equivalency.
Yeah.
I have to prove this equivalency, and I have to prove this equivalency. That is what I can do. But proving this equivalency is a twofold job, yes? I have to assume P is true, conclude Q is true, and then I assume Q is true, conclude P is true. So two theorems, so it's 6 theorems. If I want to show that these three statements are all equivalent, yes? But now, okay, now I want to hear from.
But now if we prove that P and Q are equivalent, and that Q and R are equivalent, then from that we can conclude that P and R should also be equivalent. Or we can it's like if we had X is equal to Y is
so that's
equal
one
to C, then we of course know that C is also equal to Y.
So if P is equivalent to Q, Q is equivalent to R, that's true, yes? But there's also a simpler way. Instead of proving 2 here and 2, of course the number of theorems probably will have to prove or will be the same. So, but I would say that we can go from P to Q, and then we can go from P to Q to R. Then I show that I can return back from R to Q to P. This is, but of course, you have to design these statements that this can be done easily. And I have already done that, if I remember it correctly.
What?
Yes? So here, I want you to understand that if I do this, if I show P implies Q, and if I show Q implies R, and if I show R implies P, then I am done for proving all equivalencies. Is that right? And is that understandable? Because my point, so I have already shown that, I have already shown that, for example, if I succeed to do that, I have already shown that P implies Q. But my point is to show that Q also implies P. Why this is done by this method? Because Q implies R and R implies P, so it means Q implies P. Okay, so this is a nice way. I wanted, the reason that I structured it in this way is actually this idea that I want you to learn. So if you want to prove that a bunch of statements are all equivalent to each other, of course you can do it case by case, or this is a very better way of doing it. It's a circular sometime. It's not a circular argument, I want you to understand, but I start from one, I conclude the other one, I don't worry to show it the other way around. I go to the next one, and then I show that the last one will imply the first one. I want to first make sure, do you feel the logic is the same? Everyone agrees? Yes or no? Yes? Okay. So here, if you don't mind, we can call, so we want to prove this. We want to prove that statement number 1 implies a statement number 2, and I want to show statement number 2 implies statement number 3, and I want to show that this implies statement number 4, but this is not finished. I have to show that statement number 4 also implies statement number 1. But from logical point of view, you have to be very careful. Because when I want to show this first question mark, I have only this assumption in my head. I'm not allowed to use anything else except this 1. When I want to conclude 2, the only thing that I have is 1. When I want to prove 3, don't think you have 1. You have only 2 in your hand. And then you want to prove 4, you have only 3. And when you want to go back and prove 4, you have only 4 in your hand. You have to respect this logic. Otherwise, it doesn't work. Okay? So now let us try to do it together. I hope that I have arranged them in the right way. But
How do we?
so let us do, for the time being, I want you to tell me, how can I go from 1 to 2? So I give you a parallelogram, so you know that. So what is your assumption? Your assumption is that ABCD is indeed a parallelogram. You are supposed to show that AB is equal to BDC and AD is equal to BC. You want to show that.
How do we define a parallelogram, or what's
No, we
information?
define the parallelogram. The definition is a pair. A parallelogram is a quadrilateral having a pair of parallel lines.
Okay, so the first statement is basically says that AB and DC are parallel. And
Parallel.
AD.
Yes. So it means that
Okay.
because I know 1 is true. So what I know that this is, by the way, very important. Not because this theorem is hard to prove, as you see, it's very easy to prove. But the main thing is to understand the logic behind that and how it works. So here, when I say I know 1 is true, I know that this is a parallelogram. Based on the definition of the parallelogram, I know that this one is parallel to that one, and this one is parallel to that one, yes? So what I say, if I want to be very careful, I would say that since ABCD is a parallelogram, what can I conclude? AB is parallel to ABCD, yes, to CD, and AD is parallel to BC, yes. Yes, we know. Okay. Only you have these 2 assumptions in your hand, and then based on these assumptions and what you have learned so far, that's also possible. You should be able to use them. What you have proved so far, you should be able to conclude that the length of AB is equal to length of DC, and the length of AD is also equal to the length of BC. Okay, do you have any proposals where to start?
Yeah.
You might need to add something, a line segment somewhere, yes? Do you have any idea?
I was thinking of angles. You could add angles.
Yeah, angles is a good starting point, yes? Because we know, for example, that these 2 lines are parallel, and then we see that this is a transversal. So, for example, we know something about these 2 angles. They are, but that is a good start. But what is this? What is the grand picture? Why this is useful? Do you think? So I don't know. I just want to wait to hear from you, because this problem is simple. The reason that I brought it up so carefully, because I really want you to understand this logic to prove equivalency of a bunch of statements.
Jag tänker på det.
Because you want to prove, I don't want you to. I want you to really understand what we have in our disposal is the congruency of triangles. Yes. If you want to prove that 2 sides somewhere are equal, one possible scenario is to have 2 triangles and try to show that they are congruent. And if they are congruent, I can conclude equality of sides. That's a reasonable to start. So what's the?
Yeah, just connect the MB.
Yeah, this seems reasonable now. Yes. Yeah. Okay. So what I do, which one you said? For example, let us connect join A to C. So we say that again. This is added, so you have to explain. We join A to C. Okay. Now then what? Can you complete the argument now?
We know that. I mean, I guess we have to.
So we have a Z shape here,
Yeah.
or upside down Z shape.
Okay.
So what's the conclusion?
So
Oh yeah.
This angle that I call it A1
it's equal to a C.
is C1. Understandable, yes? That is your Z shape, of course. Whenever you have a Z shape in any direction, N shape or whatever, these two angles are the same. Yes? And then do you see another Z shape? And this is actually N shape now, yes? This one. Yes? So what can I conclude now?
That A2 equals.
I can conclude that this angle, A2, is equal to what? C2.
Oh yeah.
And then, I hope that you agree with me that this triangle now is congruent to this triangle. Yes? Why is that?
Angle,
Based on what?
angle, side angle.
Angle, side angle. Because I have two angles from one triangle with two angles and another triangle, and then you see that this blue line is in common. That's exactly the same. Yeah, so I would say that. Okay, so now you know that. So let me just don't write to not waste the time. I want to go faster. But in the exam, you have to write all these days. Yes. So you can say that AB is parallel to DC and AC is transversal. You can conclude these two angles are the same. You should write that these two are parallel. This one is transversal, and then these two angles are the same. And then you write that this triangle is congruent to that triangle. So I just skipped all of them, okay? Because that they are simple. So I would say that a triangle ABC is congruent to triangle what? ADC. By the way, if I want to respect, do you remember I told you that whenever you, in principle, if you want to be very strict, when you write congruency, you have to respect to write the corresponding ones in order. Yes? So can you tell me, if I choose A, B, C as my order for the top one, what should be in principle the order of the second one? Yes? So from the top one, I choose A first, B second, and C third. Okay, so what should I choose for A here from the bottom one?
ACD.
So if I choose A from the top one, I should choose C from the bottom one, yes? Because these angles are the same. And if I choose B, then probably you understand that, of course, if I choose C at the end, I have to choose A here. And then, of course, what is left is D. But that's the correct way. But I really don't want to distract ourselves because of these nuances, yes? Okay, so what we do here, I can conclude this. Whenever I have this one, then it is clear that AB should be equal to what? CD. And, this is, by the way, means and the other ones, so what AC is also equal to BD, yes. No, AD is equal to BC. So you see, the geometry is actually very, very simple. By the way, I don't know why you missed to tell me to do this. But anyway, the geometry is extremely simple. So from now on, whenever I have a parallelogram, I not only know that the sides are parallel, but I also know the opposite sides are also equal in length, which was, of course, very trivial. Everyone knows about it, yes? But this is the proof. Any questions? Okay, now the point is this. I want you to see that if you understand the logic. The next step, I have to assume 2 is true. I don't know anything that it is a parallelogram now. I'm assuming 2 is true. I want to convince myself and you that 3 is also true. So do I know my quadrilateral is a parallelogram now?
No.
No. What I know that I have a quadrilateral. In that quadrilateral, AB is equal to CD, AD is equal to BC. This is the only thing that I know. And then I want to prove that the opposite angles are also equal. Okay, if you want to prove this, I don't know, if you start with a completely random quadrilateral, then it would be very disturbing because a random quadrilateral does not enjoy these two properties. We know that at the end it will become a parallelogram, so it might be better to draw a better picture, yes? But it by no means it means that I know it's a parallelogram. I know at the end it will end up to be a parallelogram, so I will not make life harder for myself by drawing a random object there, okay? So what I do, I will draw something similar, I would say, to a parallelogram so that it is plausible to assume that AB is equal to CD. So what I know is that this side is equal to that side. Still, I don't know if this is a parallelogram or not. And I know that these two sides are equal. Based on this, I want to conclude that A is equal to C, and I want to conclude that D is equal to B. Okay, what do you say? So you see, in this picture, in the beginning, I knew these are parallel, I knew these are parallel. In this new setup, I don't know if they are parallel, but I know that they are equal in size. Then I want to conclude that A is equal to C, B is equal to D. So what should I do now? Just concentrate, for example, in one pair. So use your energy to prove that, I don't know, A is equal to C. Extremely simple, yes? Rasmus, do you want to say something?
Yeah, we sort of do the same thing. The previous one, we connect two opposites, A and
So
C.
so you say you write it down. I'm lazy to write it down, but in the exam you shouldn't be lazy. So I would say that I join A to C, and then what? These two triangles again are congruent, but from a different theorem.
No, SSS.
SSS, yes? Okay, so here we know that this side is equal to that side. Based on this assumption given in number 2, I know that this side is equal to that side. But I know that this green one is in common between these two triangles. Then again, I have the congruency of triangles. So this means that this side, this angle should be equal to this angle. So then I don't know, what do you want to say about the other angles? Might be you say that, okay, I will change my strategy and connect these two, or can we cook up an argument that this is still the case? So immediately we realize that this angle is equal to that angle. But of course, because these two triangles are congruent, this one is equal to that one. This one is equal to that one. So this means the total angle and the total angle here are the same. So I really don't need to draw the other one. By the way, what is the name of this line when you connect the opposite sides in a quadrilateral?
No.
These are sides, but the ones that connect the opposite ones is called a diagonal. Yes? So that's a diagonal. Okay, so that is also clear now. So you see, when I wanted to prove number 3, I only assumed number 2. Not number 1, okay? And then I want to prove number 4. The reason that I have put a star on it, because it is extremely useful, not because it is hard. Yes? Now I want to go from 3 to 4. So what do I know for this one, 3 to 4? So how should I prove that? I have a quadrilateral. I don't know if it is a parallelogram or not, but I know that the opposite angles are equal. So then again, based on the same idea, I draw it like a parallelogram, but I do not claim it's a parallelogram right now. But what I know that this angle is equal to that angle. I know that this angle is equal to that angle. My goal is to show the opposite, the AB and DC are equal and parallel. So how can I do that? So I have a quadrilateral with these properties. You want to prove that AB is not only equal to DC, but it's also parallel to it. So how can we do that right now?
The same thing again.
Yeah, can we
Connect two of them and then you have angle side angle.
But like,
Okay, so let us see what theorems are involved. I want you to name them so that I want to make sure that you really
Okay,
understand what's going on. So your idea is to join A to C, for example.
Yes.
Okay, and then defend yourself.
Okay, we can't conclude that these are. I mean,
So how can we conclude? You see, the only thing that I have in my hand is equality of these two angles, equality of these two angles. And now, are you going to show that they are equal? I don't know. That's you have to defend yourself.
yeah, because like I don't.
Okay, let me do this. I will pause recording video for a while. I want you to write it down. So when I ask you to tell me, you can just tell me from your writing or whatever. Okay, think a little bit about that. So what you have, you only know that. Let me just clean this. If you want, you can add it again later. So what you have, you know, I have a quadrilateral. I don't know at all if it is a parallelogram right now, but I know that this one and that one are equal and these two angles are equal. I don't want to prove that this is a quadrilateral. I want to prove that AB is equal to DC and parallel to DC. Yes? My personal impression is that proving these trivial ideas are harder actually sometimes. What happened? No, because let me guide you. Because if you want to do mathematics Olympiad, you have to be very good in deciding what to do. Yes. So far, if you, I don't know, this is also good for your memory. If you review, how can we? So this is your strategy. You see, you shouldn't do things randomly. So you want to prove, for example, AB is parallel to CD. What are the tricks that we have? What are the techniques we have so far? If you want to show that two lines are parallel, more or less in this setup,
We would want to like show that the angle of D is equal to 180 minus the angle of A.
why? So
Because if they were parallel, then AD would be a transversal.
Yeah, exactly. So that is the converse theorem of this corresponding angle axiom. So I told you that. Do you remember? This is important to think in this way, yes? I told you that if you know two lines are parallel, another line cuts them, then this angle and that angle are equal. So this means that this angle and that angle are supplementary, yes? Because they are adding to 180 degrees, and this one is equal to this one, so that one and that one are supplementary. They add to what supplementary means they add to 180. But I told you that the converse of this one is also true. So if you have two lines, but you don't know if they are parallel or not, but a third line cuts them, and for some reason you know that these two angles are the same. What can you conclude about the lines? You can conclude the original lines are parallel, yes?
Yeah.
So this you need to think in this way. So if you want to prove two lines are parallel, you should have a strategy how to do it. So now you at least understand that you have to do something with angles, which is very good, yes? Because what we know is about something about angles. So now can you tell me? Can you tell me why this is parallel to that one? If I succeed to show this one plus this one is how much?
180.
If I can show this one plus this one is 180, this means that this one and that one are equal. And this means that again I have my Z shape. And I can conclude the lines are parallel. Yes or no?
Yes.
Understandable? So this is, I would say, this is my strategy. Later, we will learn other tricks to prove two things are parallel, two lines are parallel. But so far, this is the only trick that we have. So you have to use it. But now you see the problem becomes extremely simple. Why this and that add to 180? Because we know that in every quadrilateral, whatever it is, the sum of the interior angles is 360 degrees, but they are equally pairwise. So we know that whatever the quadrilateral is, parallelogram or not, I know that the angle A plus angle B plus angle C plus angle D is equal to 360 degrees. But now you are telling me that A and C are the same. So instead of C, I write A. And A plus A is 2A. And then you are telling me that B is equal to D. So instead of B, I write D. And D plus D is 2D. And this is 360 degrees. And then you divide by 2, so the angle A plus angle D is 180 degrees. Yes? And then if this angle plus that angle is 180 degrees, that is enough to conclude that these two are parallel. Do you understand the last step or not? I want to conclude from here that AB is parallel to DC. The reason is that if I have two lines, which I don't know if they are parallel or not, but I know that this angle is equal to that angle, then I am done. Or if I know that this angle and that angle are supplementary, then I am done. And I was able to show that this angle and that angle are supplementary. So you see, if you want to extend your point of view, you need to think in this way. This is a line, this is another line. I don't know if they are parallel or not, but I know that this third line cutting them, this angle turns out to be equal to that angle. Then it means that these two lines have to be parallel. Yes? Understandable or not? Okay. So you see, at least AB is now parallel to DC. And do I know its parallelogram? No, I just know about some information about the angles. Okay, but that is one thing left. I have to prove AB is also equal to CD. Now, if you want to, you can use parallelness.
Yeah.
Yes?
Oh yeah, because yeah, we can do the exact same thing.
Yeah, now we can do exact same thing, yes? I can say that now I join A to C because I have some extra information in my hand now. I not only know about the equality of paired angles, I also know that these are parallel. And now if I join them, what can I say? I can say this is parallel to this one. Now I know it.
Yeah.
And this is transversal. This is my Z shape now.
Yeah.
So this angle becomes equal to that angle, yes?
Yes.
And then what?
And the other angle.
And then I have another Z shape, yes?
Yes.
What is that Z shape, by the way?
M shape.
Do I have it right now?
Yes.
What is the Z shape?
Or
D
can
to A.
can
to
we
C to
just use the
No, I want to see. Do I have another Z shape right now? Which one is that?
The one that looks like an N. D to A to.
You mean this?
Yes.
No.
What?
I want you to understand. I don't know if they are parallel right now.
well, but we can we just do the exact same reasoning?
Aha, so we have to do something more.
Well,
But right now, we do not know that these are parallel. What I have shown are that this is parallel to this one. So if you want to say that I have another N shape, this is not still an N shape until I prove AD is parallel to BC. But this is possible to do, yes? Instead of changing B to D and C to A, I can work with the other pair. And then this will also work. And then you can use that one. And if you use that one, then of course this one is also equal to that one, and this is in common, so they are congruent. I can conclude that these sides are also equal.
Can we just like just after we've proven that both are parallel, just use the first step?
No, be careful. No, first step means one of these.
Yeah, or say that because it's parallelogram, then we also know that.
No, we don't know it's parallelogram.
Well,
no, we don't know. That's
because we've just proven that both pairs are parallel. Which
yes,
we
yes.
defined as
Yeah, you can somehow jump
and then
conclude that one, and then come back.
That we have
that's
already
possible,
proven.
logically possible.
Yeah.
Yeah, but I don't prefer this because it would be a little bit unorganized to do that, but that's also good. Yeah, but that's completely correct. So when you conclude that AB, CD, so if you conclude this one is parallel, of course, then suddenly it becomes a parallelogram. And then you can jump to the first one and conclude the second one. Yeah, that's correct, but yeah, that's correct because we have done it like that. Okay. But that is possible even without that jump. That's what I'm saying. Okay, now the point is that we have to go back. Which is the most important part. Many times I use this trick to prove some a quadrilateral is a parallelogram. I do not prove that they are pairwise parallel. I take two of them and show that they are not only parallel but also equal in size. Then I can conclude that if we can show that we can jump from 4 to 1, then we are done. So now let us just do the last one. So we have 4. We want to convince ourselves that we can jump to number 1. So what do I have in my disposal right now? I have a quadrilateral. I draw it again as if it is parallelogram, but I really don't know. Okay? So we pretend that we don't know it's a parallelogram. So it's A, B, C, D. What I know is that AB is not only equal in size to CD, but it is also parallel to BC. And then I want to prove that this shape is indeed a parallelogram. There is one more thing to show. What is that thing?
But the other sides
Are also
parallel.
parallel. Because if I want to show that a quadrilateral is a parallelogram, I have to show that they are parallel, but I don't need to show. This is given. I have to also show that these two are parallel. This is the important thing that I have to prove.
Oh yeah, so
The only thing so you need to understand, you reduce your problem to proving the parallelness of these two sides, and then you are done. So can I prove that?
or so yes, so we need to say that angle D plus angle C should be equal to 180 degrees, or
So yes, you can use the parallelness of these two in any way that you like to. But then at the end, you need to prove that these two are parallel. So don't you think it's a good idea to join A to C, yes? If I join A to C and I can convince myself this angle is equal to this angle, then I am done. Yes?
yes.
Because then I have the real N shape here. This is not a real N shape until I prove that. Of course, if you are in a primary school, might be you write like N like that, I don't know. But this is not a real N, yes? The real N, you have to keep these in parallel. Okay, so if this is a real N, I have to show that these two are equal. This is one way to show that these two lines are parallel, yes? If I ask you what I am using in this argument, you should tell me the converse of the corresponding angle axioms, yes? So, okay, can you tell me how can I do that now?
Well, maybe this method is a bit ineffective, but we have a C shape now and two parallel lines, so we know that at least A1 equals C1.
So what is your strategy? Is your strategy to show congruency of triangles somehow?
No, not really, but I mean, I want to prove that, okay, well, it's kind of hard to explain, but we know
No, it shouldn't be hard to explain, yes?
that,
If you want, I can just give names. If you want, I think everything is named now.
well, okay, so what I want to do was extend the line AC.
Okay, so before doing that, let us see, without extending something, we can do it. So I will pause the video and I want you to think about it.
With the brute force.
You might be very sleepy. This is a very simple problem. Why don't you see it? So, yes?
First, you can lengthen AE.
AE?
AB and CD. So you enlarge it so it gets longer.
Okay, so to where? AB extended to where?
Any length.
Okay, so any length.
And on the other side as well.
Okay,
Same thing for CD.
yes.
And now we can conclude that that there are corresponding angles in BD.
Here and there?
No, near B and D.
You mean this angle and that angle?
No, B and C.
Ah, okay. Yes, B and C.
Yes,
They are equal.
yes.
Yes, because I know this is parallel to this one, this is transversal, so this angle and that angle are equal, yes. Then?
Yes, and C and D also have corresponding angles.
You mean this?
Now we can draw a diagonal.
What you can see now? we still don't know if they are parallel. Because this is one dot, this is double dot. Unless you prove double dot plus dot is 180 degrees. Yes? I don't know. Can you see? So I mean that I'm listening to you. If you can continue, I'm listening. So what you have told me, these are the consequences. Do you agree with me?
Yes.
Okay, now if you can go forward, please just go. No, okay. So what is your idea?
It's incredibly simple, really.
Incredibly simple, yes.
Side angle side.
I don't know why are you getting so confused.
You just connect, if you do it again, we connect A and C.
Yeah, we connect. I did it. You didn't
Yeah.
respect that.
And then,
So we join A to C.
yeah. And then,
Okay.
we
Do I have a real Z or N shape
Yes,
right now?
We have a C shape.
Yes, because this one is parallel to that one. So what can I conclude?
So that
This one
A1.
and that one are the same.
Yes, and then we have two sides which are equal.
And then we are done. Yes? Because this side is equal to that side. This is in common. And the angle between two sides are also equal. So this is SAS, yes? Two sides and the angle between them of one triangle are equal to two sides and the angle between them of the other triangle. So they are congruent. If they are congruent, then there is no doubt if this is double dot, this should be also double dot. And if this is double dot, this means that I have an N shape. And this means that these two are parallel. And then because we already know that they are parallel, so this means that this is a parallelogram. And usually this is the best way to prove that a quadrilateral is indeed a parallelogram. You just take two sides, prove them they are parallel and simultaneously equal in size. Then you don't need to be worried about parallelness of the other pair. Okay. So this is more or less good here.
Oh, wait,
Yeah.
but how we've proven that all the sides and angles are equal, but how do we go from that to that AD and BC are?
No, first of all, I didn't have these. I have this in common between the top triangle and the bottom one. I know if this is one dot, that's also one dot. And then I know that this side is also equal in size to this side. It was given from the beginning. So the top triangle and the bottom one are congruent. If they are congruent, then if this is double dot, now I can also call this double dot. And now I concentrate here. Okay? So I have two lines that I don't know if they are parallel or not, but I know that these two angles are the same, so I have to agree that they are also parallel. And then yes. Good. Okay, now let me just tell you a little bit about the diagonals of a quadrilateral. Of course, you already know intuitively. It's so simple. It's not hard geometry. Yes? Yeah. Okay, so what can you say about the diagonals? Do you think that they are in general equal in size? Apparently not, yes. If I draw this diagonal, it seems shorter, yes. And that is long, yes. But they have something, you can say something. The point that they intersect has a property. It's important to know. If you have a parallelogram, if you draw the diagonals, not in general, that is not true in general that they are equal in size, as you see they are not. Yes. But what happens if I call the intersection point, I don't know, M, for example? What can you say about M regarding line segment AC and line segment DB? Yes?
The midpoint of both lines.
Midpoint of both of them. That's important to know. So M is the midpoint of this diagonal. It's also the midpoint of this diagonal. We want to prove it. Okay? So why that's true? Now I know that the original shape is a parallelogram and I drew the diagonals, they intersect at the point. I want to convince myself that this length is equal to that length and this length is equal to that length. Just tell me, it's easy. 5 seconds only. Just tell me.
Congruence.
1, 2, 3, 4, 5. Okay, finish.
Congruence.
So congruency of what? Yes, it is. I mean, it's more or less clear, isn't it?
I mean, what I'm saying is,
So
we know this is a parallelogram, by the way. Right?
we know, yes.
Yes.
Right now, we
Yeah.
know it's a parallelogram. Yes.
We have
So what can you say about this dot here and that dot there?
they're equal.
They are equal.
Yeah.
Yes. What can you say about this dot, double dot, and this double dot?
Exactly, they're equal.
They are equal.
Yes, and then you have.
And these triangles are congruent.
Exactly.
My shape is actually misleading,
Yeah.
but that's not precise. But this triangle on the bottom is congruent to that one. Why?
Yeah. So, angle, side angle.
Angle, side, angle. Yes? These two angles, and the side between them is this side. And these two angles and the side between them is this side. But we already know this is a parallelogram, so we don't have any problems. We showed that if it's a parallelogram, the sides are equal. So these are also equal. So this triangle that you see here is congruent to this triangle that you see here, based on angle, side, angle. Yes? And then if they are congruent, then it is clear this side is equal to that side, this side is equal to that side. Yes? Is that clear? Now, what do you think? Can you state the converse theorem for me first? Because I told you that. When you prove P implies Q, there is no guarantee yet that Q also implies P. This is called the converse of this implication. When you swap these, this is called the converse. If the statement is the implication true, there is no guarantee the converse is also true. But if the converse is also true, there is no difference between P and Q in mathematics. Yes? So if I showed that if ABCD is parallelogram, I showed that diagonals bisect. I'm just making it very short.
Yeah.
Okay? So what is the statement of the converse statement?
If the diagonals in a quadrilateral bisect each other, then it's a parallelogram.
It's a parallel. So the converse statement, it might be true or might be false. Be careful. So if in a quadrilateral diagonals bisect each other, the quadrilateral is a parallelogram. This is the converse statement. It might be true at this point or might be false. I want to see how do you think about it. Do you think it is false? If you think it is false, you need to convince me by giving some kind of example, which in mathematics is called a counterexample. Yes, I have talked about this several times. But if you want to defend it, you have to have a reasonable argument for it. Okay, you cannot prove it case by case. You have to have an argument that covers everything, every quadrilateral, every shape with that quadrilateral. Okay, so are you against it or in favor of it? Do you think it is false if I go the other direction, or it is true?
It's true.
Okay, so if you say true, you need to defend yourself. Yes.
Okay.
So what I have, I draw a parallelogram, but I don't know if it is a parallelogram.
Yeah.
I pretend that it is not, if you say that this is the case. So what I know, I draw the diagonal. What I know they intersect at a point.
Yeah.
I know this one is equal to this one. This time I know they are the same.
Yes.
And I know these are the same.
Yes.
I want to show that the original quadrilateral is a parallelogram.
The angles on M are
Yeah, that's finished, yes? Because now this angle and that angle are the same because they are vertical angles,
Yes.
opposite angles. So it means that this triangle on top and this triangle in the bottom are congruent. Yes? Because of side, and angle between them. And now they are congruent. What can I conclude? Can you tell me? One thing becomes clear. This side becomes equal to that side. But what else?
they're parallel
They are also parallel. Why?
because the angle.
Because this angle, if this is one dot, this is also one dot. So this means that I have my real Z shape. So these two sides are not only equal in size, but also parallel. And then I told you that this is important. If two sides are equal and parallel, we can conclude that it is a parallelogram, yes? That's that. So remember this fact as well. Okay? So if I go to a rectangle, what happens? If I go to a rectangle is a parallelogram. So it means that whatever you showed for a parallelogram is already there, but it might happen that you have extra properties. One of the extra properties is that, what can you say about the diagonals in a rectangle? Every property that you had, they bisect each other.
Yeah.
So we know that this one is equal to this one. We know that this one is equal to this one.
Yeah.
For example, why? Because it's a parallelogram. And we showed that. But can I say something more in the case of a rectangle in particular?
They're all equal.
They are all equal in this case. So I don't need to put double dashes, yes? All these parts are equal. Because the diagonals are also equal. But why the diagonals are equal in this case? And by the way, why 4 angles are 90? Because do you remember how I defined the rectangle? I defined the rectangle to be a parallelogram containing one 90-degree angle. But why? But you know what is a rectangle, yes, from childhood, yes? So you know that all the angles should be 90 degrees. Why?
Why all?
Well, yeah, because if all the angles should add up to 360 degrees. And we know it's a parallelogram, so we know that the opposite sides angles are equal to each other.
No, don't make it hard.
Then
If this angle is 90, these are parallel.
yeah,
This
yeah,
angle is
parallelogram.
also 90.
Yeah, of course.
So these two angles are 90 and 90. Yes? And then you can repeat this process. So everything is 90. And now if they are 90, so why these two diagonals are equal? Can you tell me why?
They're congruent.
So the congruency of what? If you don't mind, let me name them so that you can name it if you want to. So A, B, C, D. Why AC is equal to BD?
Well, we know that all the angles are 90, first of all, so let's, like, the angle on D and the angle on C are both 90.
Mm-hmm.
Yeah.
So you mean this angle
Yes.
and this angle are 90?
Yeah.
Yes.
And because it's a C shape as well, so we know that.
No, easier than that. You see, this side is also equal to this side because that's a parallelogram. And so I concentrate on this right angle triangle here.
Yeah.
Yes? And this right angle triangle here.
No, they share.
This is in common.
Yes.
Yes? And then this is equal to that one, and the angle between them is 90. So this right angle triangle is congruent to this right angle triangle, so the hypotenuses should be equal. Okay, so that's also true. Yeah, so there are many theorems that they are trivial. The important thing I wanted to go through it in detail because I really want you to understand the logic of how to prove equivalency of several statements. And that was actually, even though it was very, very simple, but I believe it teaches you a lot of mathematics. Okay, so now, I don't know in which direction should we go. I will write 2 problems. They are nice problems, by the way. I want you to think about them for the next time. And then I had given you 1 problem, so we will continue solving problems next time. But it is important you think about the problems, okay? So I will write them here, and if we have time, I want to go back to a very important theorem that I realized that I haven't talked about for triangles, and that is called Hinge Theorem. So I want to talk about that one if we have time. So I should have started with that one before jumping to quadrilaterals. Okay, sorry. Okay, so here, So I want to. Two problems for next time, okay? Definitely I will start solving these two and the previous one and the beginning of the next session. So, problem 1. Consider, I don't know if I can state it properly, consider 3 circles with the same radius, size. I mean, the size of the radii are the same. So consider 3 circles with the same radii size. I don't know if this English is correct or not. Yeah, something like that. Okay, that pass through a fixed point A. Of course, I am talking in planar geometry, so everything is happening on one single plane. Show that all other points of intersections of these circles lie on a circle with the same radius. As the 3 circles.
Okay, so all of the points besides A lie on a circle.
Yeah, so you have a point here. I don't know how can I draw it usually. I have a circle here, another circle that passes through with the same radius, and then I have another one that passes through this one, and then I have another intersection points. I want you to prove that these intersection points also lie. Every other intersection points also lie on the same, not on the same circle, on a circle with the same radius. Something like that.
Wait, and they
But then,
all,
of course, I have freedom because
And
they
they
can
all-
move around. Yes, I
they
have
all
infinitely
meet-
possibilities.
they
Yes.
all meet in the middle.
No. I don't know how to draw it, but you need to consider all possible scenarios. So might be I can draw it inside here, and then I will have another intersection point. So it doesn't matter.
Or where is A in this?
A is here.
Okay, so they all meet in the middle. There won't be a small,
I don't understand what you mean in the middle.
or like in the center of.
So I mean that consider you have a fixed point,
They'll
and
meet
I
at
give
one
you
point.
3 circles of equal size. You put them on this point somehow that pass through this one. Then they will intersect at some other points.
Yeah.
You want to show that those other points lie on the circle,
Okay.
but with the same radius. Okay, so then another problem is actually interesting. So I got it from the same book. I will write the name of the book as well here. So this is also something that I think you will like. And then you have now enough experience if you have done. So problem, I think this should also be beautiful. I haven't checked the solution at all. So let f, so I don't know, but might be the idea is the same. Let f be a real valued function. So you know about these things now. I don't want to explain more. So let f be a real valued function on the plane. So it means that it takes a point from a plane, gives you back a real number on the plane, such that for every square A, B, C, D, f of A plus f of B plus f of C plus f of D is equal to 0. Show that f is a constant function. So it's very close to the previous problem. Show that
Yes.
f is a constant function. So if you have a little bit problem understanding this, you need to check the previous video. So I know that I have a real valued function, acts on the points in a plane, but for every square you can choose on the plane, this is the relation that if I add f at those points, they add up to 0. We want to prove that that's a constant function. So these two problems, as well as some of my presentations, have been taken from the book Plane Geometry.
So probably some-
By Amol, if I can pronounce it correctly, Sassani. Yes. It's a good book, so I will actually use a lot, extensively from what he has written. So plane geometry, Amol Sassani, these two problems are there. And some of my presentations are also following that book. Okay, so I think these are nice problems in that book. And then you can solve them based on the information that you got today. And of course, understanding of what a circle is, yes? We have a little bit of time. I don't know if I want to show. So let me just stop quadrilaterals here. And let me at least talk about the Hinge Theorem. I don't know, for some reason, it was not in this book, so I forgot to talk about it when I was talking about triangles. Okay, so let me now at least I can state the problem. It's a very intuitively clear theorem. And this tells you that if I have two triangles, so I want to draw them somehow. So if I have a triangle, let me just draw it like this. A, B, C, D. A, B, C. And then I want to keep the other one the same size. So I don't know if I can draw it. So I want to keep it the same size. And I call it A prime, B prime. But I want to make the angle smaller than this angle, and I want to keep the length the same. So it would be something, I don't know, like that. So something like this. Yeah, I don't know. So what I want to tell is that I want to keep this size and that size the same. I want to keep this size and that size the same. And of course, the angle A prime, I want to make it smaller than angle A. Yes? But then I want to say something about the length of the third side. What is intuitively correct? If you compare the length of this one and this one, how they are related? Yes?
They're the same.
No? Because the angle is smaller.
It'll be smaller.
Yeah, B prime, C prime is smaller than BC. Intuitively, it seems that if I make this angle smaller, it's like a hinge, you know. So if I make this angle smaller, we want to prove that B prime, C prime is also less than BC. This is called the Hinge Theorem.
Can you extend that to make otherwise isosceles?
Yes? It's intuitively very clear. If I keep the sizes the same, I compress it. Of course, the third side would be short. But why? And the proof is very nice, actually. This is why I want you to see it. So let me just explain it for you. We have enough time. So what we do, because this angle is smaller than that one, I draw a line, a ray here, so that, for example, let me see if I can do it more or less properly. Okay, so I draw a ray, call it AX, so that this angle becomes equal to that angle. This is possible. Yes, because I am assuming that this one is bigger, so I find some ray somehow. And by the way, we learned how to draw it. Do you remember? We learned how to produce a given angle by the compass and straight edge. So I can reproduce the angle if I want to. And I reproduce it here. If you have forgotten, you can check one of the previous videos. Okay, so anyway, this is clear that I can draw a blue line here so that this angle becomes equal to this angle. And because this angle is assumed to be smaller, this becomes inside this angle somehow, yes? And now what we want to do is a little bit strange in the beginning. I take this angle and draw the angle bisector. Yes? The angle bisector of just this orange part. Yes? And then I call this D. So what I know, if this is alpha, this is also alpha based on my construction. Oh, sorry, before doing that I had to do something. I had to choose a point on the blue line so that this is equal to that one. Okay, so that, sorry, I was a little bit ahead of myself. So on this blue line, I will choose another point here. I don't know, for example here. I will call it C double prime, so that AC double prime is equal to A prime C prime. This is what I do. I draw this blue line so that this angle becomes equal to that angle. Then I separate, I just find a point on the blue line so that AC double prime is equal to AC prime. And then what I do, I actually connect this to here and connect this to here.
What?
Okay? So is that understandable? So I just drew this blue line. You have to explain all of these things when you want to write it in exam. And then what I do, I draw this one so that this angle becomes equal to that angle. This is possible. And then I choose this point so that this length becomes equal to that length. So automatically these two become the same because they were the same in the beginning. And then I draw the angle bisector of this narrow angle left over so that it goes and intersects it at D. And then I connect C double prime to D and B. Okay? But what I want you to tell me, case by case, do you agree that this triangle, constructed in this way, is congruent to this triangle? And why is that? It's clear, yes? AD is in common. Angle alpha and angle alpha are the same based on my own construction. And then AC double prime, I separated it in a way that it becomes equal in size to this one, but this one was originally equal to that one. So they are equal. So this means that these two narrow triangles are congruent. Yes? If they are congruent, I hope that you agree with me that this little part here, C double prime D, is equal to DC. Yes? And now, let us go here. Let us go here and write the triangle inequality in this triangle. So what I know that BD plus DC is larger than BC double prime. Do you agree? In this triangle, this side plus that side is larger than this side. But DC is equal to, no, this is not DC. This is DC double prime, yes? BD plus DC double prime is larger than BC double prime. But it was not wrong what I was writing. So this is equal to DC. So instead of DC double prime, I write DC is equal to BC double prime, yes? But now look, what is BD plus DC? Is exactly BC. So BC is larger than BC double prime. Yes? But my goal was not to show that BC is larger than BC double prime. My goal was to show that BC is larger than B prime C prime. But I am done. Why?
because A, B, C double prime is congruent to A prime, B prime, C
Based
prime.
on construction, yes?
Yeah.
Because this was equal to this from the beginning. This one, I chose it equal to this one myself. And this one, I chose it equal to this one myself. So now this triangle that you see here is congruent by my construction to this triangle. So this means that this one is equal to that one. And when I showed that BC is larger than BC double prime, it means BC is also larger than B prime C prime. So this is a simple, intuitively simple, but it's a little bit convoluted if you want to really prove it. And I want you to think about the converse. Please state the converse and prove it. The converse is also true. Okay, so this is also an exercise, yes? State the converse of the Hinge theorem and prove it. This is simple. I call it exercise, but the other ones are actually quite a little bit, it needs a little bit of work. Any questions? Okay, so next time I will start with solving some problems first and then we continue. I want to accelerate a little bit our speed because I want to reach to very interesting things. Geometry is very, so these are always, we are proving trivial things. So I'm just constructing your logic, but then later we want to really prove interesting and nice, exciting problems. Yes?
Mm-hmm.
Thank you very much.
Yeah.